So we're getting started with chapter 4 today, which discusses cycloalkanes and conformational analysis of cyclic systems. Now, we've discussed open-chained or linear compounds at this point, but many organic compounds of interest contain rings of carbon atoms, or cycloalkanes. A cycloalkane is formally defined as a saturated cyclic hydrocarbon. Cycloalkanes, in their simplest form, have a general formula of CnH2n. Cycloalkanes are named the same way as straight chain alkanes, however you add the prefix cyclo. So for example, we have cyclopropane here, which is C3H6, cyclobutane, which is C4H8, cyclopentane, which is C5H10, and cyclohexane, which is C6H12. So notice the only thing that's changed for naming cyclic systems is that we've added the cyclo prefix. Does this make sense to everyone so far? Is everyone comfortable with this idea so far? So continuing on, let's talk a little bit about naming cycloalkanes. The parent chain is named the same as a straight chain alkane, but with the prefix cyclo. So following our naming and numbering method from our nomenclature section, first we find the parent chain, which indicates and is indicated by the total number of carbons in the ring. Then you number the substituents by positioning them at the lowest carbon number. So for example, we'd prefer to count clockwise in this case rather than counterclockwise because we get lower carbon locant numbers for our substituents. So this compound would be named as 1,3-dimethyl cyclohexane rather than 1,5. Again, just like always, we're aiming for the lowest set of carbon locant numbers in sequence for our substituents. Does this make sense to everyone? Is everyone comfortable with this idea? Can I get some responses in the chat just to make sure everyone's following so far and can see the screen so far?
Yeah, it's not bad.
Okay, perfect. So let's look at another example. So in this case, we have multiple substituents, and as a result, we have multiple choices for where to begin our counting and in what direction to count. So starting off at one of our methyls, we'd end up with a methyl at the 1 position, a methyl at the 4 position, and an ethyl at the 2 position. Okay, let's look at our other options. If we start counting at the ethyl group and we count clockwise, we end up with an ethyl at the 1 position. However, even though we have a methyl at the 2 position, we've ended up placing a methyl at carbon number 6. And that's a pretty large locant number. Alternatively, if we start counting at the other methyl, we end up with 1 methyl, 3 ethyl, 4 methyl. So we choose the numbering method and counting method that gives us the lowest locant numbers in sequence. So all of these structures have a locant number of 1. Some of them have a locant number of 2, and the locant number of 4 is the smallest possible locant number that we can have for our third substituent. So we'd name this compound as 2-ethyl, 1,4-dimethyl, and then since this is a 7-carbon chain, we'd call this cycloheptane. Does this make sense to everyone? Any questions on this example? If not, let's keep going and let's talk a little bit about Cis Trans Isomerism in cycloalkenes. Now, remember in our traditional discussion of linear species, we noted that for linear compounds, we can have rotation about the carbon-carbon bond. Now, cycloalkanes are less flexible than open chain alkanes because the ring structure in turn prevents free rotation of our single bonds. We can't rotate our carbon-carbon bonds. They're locked in place as a result of this ring system. And we can showcase that quite clearly if we just sort of compare models for our two different if we compare a cyclic to an acyclic system. So allow me one moment to put together a model, and then I'll show it to you using the camera feature. It's always a little tricky getting the bonds to cooperate when you're making a cyclopropane structure. So let's look at a cyclohexane just for comparison. Okay, so let's look at our typical acyclic system, our linear system. Does everyone notice how I can freely rotate about my carbon-carbon bond? Does everyone see how I can freely rotate about my carbon-carbon bond? And I have a lot of flexibility across my carbon-carbon bond. Does everyone see that? Okay, now let's try to do the same thing with a cyclic system. So if I try to rotate about my carbon-carbon bond, do I have as much freedom of rotation? Am I able to get much freedom of rotation? No, we're locked in because the cyclic system has certain geometric requirements in terms of how the bonds are arranged. No matter how hard we try, we can't rotate fully across our carbon-carbon bond. The ring limits our flexibility. Does that make sense to everyone? Okay, so what's a consequence of this? What's the issue with that? Well, what this in turn means is that cycloalkanes have two distinct faces when viewed edge on. And in turn, we have unique stereoisomers depending on the arrangement of substituents in our cycloalkane. So stereoisomers are compounds which have their atoms connected in the same order but differ in three-dimensional orientation. The most common form of isomerism is Cis Trans Isomerism, where there are two different substituents, and depending on their relative placement on each face of the ring, we have two different isomers. The cis isomer has the substituents on the same face. Does everyone notice how both of the substituents are on the quote-unquote top face? Does everyone see how both of our substituents are on the same side for this dimethyl cyclopropane? How they're both quote-unquote pointing up. Likewise, the trans isomer has the substituents on the opposite face. So we have one of our methyls pointing up, the other methyl group pointing down. And as you can see, do these two molecules have the same shape? If we look at their structure, is their shape the same? Looking at these two molecules, is the shape the same or different? If we look at our 3D depiction, it's different, exactly. So stereoisomers have the same formula, the same connectivity of atoms, but they have a different three-dimensional shape. Does that make sense to everyone? Perfect. So we talked about some cis and trans isomers. Let's now talk a little bit about factors that influence the stability of cycloalkanes. And the main factors that we need to consider are angle strain, steric strain, and torsional strain. So let's look at cyclopropanes. Let's look at cyclopropanes, and hopefully when I make the model using my model kit, it doesn't break on me, because cyclopropanes are not particularly low in energy, to say the least. They're not particularly stable. So the first factor that influences cycloalkane stability is what is known as angle strain. Now, what is angle strain? What is angle strain? It can most simply be defined as the distortion of bond lengths and angles from our ideal bond length and angle. And we call this phenomena angle strain. So we know that a typical sp3, if we have an sp3 carbon, the bond angle is going to be about 109.5 degrees. Well, if we look at a cyclopropane, we have a bit of an unfortunate picture in that case, because the typical bond angle in our cyclopropane is 60 degrees. So as a result, we are distorting our carbon-carbon bond angle. And as a consequence, so if we were to look at our cyclopropane system, our carbon-carbon bonds actually bend outward from the internuclear axis. So rather than having a direct overlap, instead what is occurring is we have an overlap that is bent away from the internuclear axis. And in turn, our cyclopropane carbon-carbon bonds are heavily distorted. Does that make sense? Does everyone see how a cyclopropane would require a 60-degree carbon-carbon bond? Our ideal bond angle is 109 degrees. So in order to best accommodate and to best overlap and form a bond, our carbon-carbon bonds end up having to bend outward from the internuclear axis. And as a result, this overlap is less efficient. And the reason why this is pretty interesting is this can partially explain why cyclopropane carbon-carbon bonds can sometimes behave very similar to an alkene or a carbon-carbon double bond in terms of reactivity. Cyclopropane carbon-carbon bonds are substantially more reactive or labile than your typical carbon-carbon bond. And that stems from both a large amount of angle strain and the fact that our carbon-carbon bonds in cyclopropane are heavily distorted and, as a result, substantially weakened compared to your standard carbon-carbon bond. If you try making a model of cyclopropane, you'd immediately start to notice that it's not exactly a happy structure. Does everyone notice how our bonds are heavily distorted, and this structure, when you're putting it together, has a fair amount of angle strain? The angles required to form a cyclopropane ring are pretty demanding because carbon would much rather prefer to have larger bond angles of about 109 degrees. Instead, we're distorting our bond angles, and as a result, we end up with this almost puckering effect. Now, cyclopropanes are also unstable because they have significant amounts of steric and torsional strain, and this is really what kills cyclopropanes. The steric strain is electron-electron repulsion of atoms or groups of atoms that are too close together. So Not that we want to keep making things worse for our cyclopropane molecule, but it's important to consider what happens when we start to have substitution on our cyclopropane. Well, let's look at this example shown here, where we have two ethyl groups positioned in our cyclopropane ring. Now, this is particularly problematic in this case because if we apply what we've learned from our chapter on Newman projections, we see that there's a pretty substantial steric interaction. So if we look at our, let me try to find the best view for this. So if we look at our molecule, does everyone see our two methyl groups? Does everyone see our two alkyl groups in our cyclopropane ring? Now, does everyone notice how if we look at our alkyl groups, if we look at these alkyl groups, they're really close together in 3D space. They're almost bumping into each other, right? And so as a result, these two ethyl groups experience a steric repulsion. As both of these ethyl groups or both of these alkyl groups take up space and they repel each other and push each other away and destabilize the overall molecular structure because they're adding a substantial amount of steric strain. Does this make sense to everyone? Does everyone see this substantial amount of steric strain? How our two alkyl groups are very close together in 3D space? This is the exact same phenomena that we observed for gauche interactions, where gauche interactions are driven, again, by steric strain. Our groups, our alkyl groups and our other substituents take up space, and when those groups are in close proximity in 3D space, those groups experience a repulsive interaction. Now, what really kills cyclopropanes is torsional strain. So if we look at a cyclopropane, if we just look at a typical cyclopropane, and we look down one of our carbon-carbon bonds. So we're looking down one of our arbitrary carbon-carbon bonds. My question to, let me take the other angle. Here we go. So my question to you is, what does it look like in terms of dihedral angle? So if we look down one of our carbon-carbon bonds, like so, what do we notice about our substituents in terms of dihedral angle? Are they staggered or eclipsed? So like looking at our two hydrogens here and here. So looking at our two hydrogens, are they staggered or eclipsed? Is there a large or small dihedral angle separating them? What does everyone think? They're eclipsed, exactly right. All of our substituents in our cyclopropane ring are eclipsed because our cyclopropane ring is locked into this specific conformation. So the bonds are locked into an eclipsed conformation, and as a result, we have a large amount of torsional strain. So as we can see, if we look at a cyclopropane molecule, we can't rotate our bonds, right? We're sort of stuck in that respect. We don't have a lot of freedom of rotation. So in turn, if we look at our bonds, we're locked into this eclipsed conformation, and we have multiple highly destabilizing eclipsing interactions. There's a 0-degree dihedral angle separating our substituents. And as a result, cyclopropanes have a substantial amount of torsional strain. Does that idea make sense? Okay, so let's keep going now. Now, whenever there is distortion of bond length and angles from ideal, there are the following factors that we have to consider. So strain, such as angle strain, increases the potential energy stored in the bonds of our molecule. Increased strain is destabilizing, and strain in turn increases the reactivity of our molecule. Now, in response to this angle strain, molecules will distort and adopt conformations to minimize strain. So when you start to get to rings larger than 3 atoms, they are not flat. Cyclic molecules will assume non-planar conformations to minimize angle strain and torsional strain through a process known as ring puckering. The larger the ring that you have, the more possible conformations there are to analyze. We'll be focusing a lot on cyclohexane ring systems as they're prevalent in many organic molecules, and understanding their different conformations can help us understand patterns of reactivity and stereochemical preferences for these cyclohexane systems in chemical reactions. Okay. So let's talk about our larger ring sizes. Let's talk about our larger ring size. And just to recap for cyclopropane, it's a 3-membered ring with a planar structure, has carbon-carbon bond angles of 60 degrees, and it requires that our bonds are bent. And as a result, our bonds are weaker than usual due to this inefficient overlap. Now, as we discussed in our conformational analysis, cyclopropane has significant torsional strain as the bonds are locked in an eclipsed conformation. We have a 0-degree dihedral angle separating our substituents. And as a result, we experience a substantial amount of torsional strain. And this gets worse when you have substituted cyclopropanes. Does this make sense so far? Does this idea make sense so far? Okay, so moving past our cyclopropanes, we have cyclobutane. Cyclobutane has less angle strain than cyclopropane, but it has more torsional strain due to its larger number of ring hydrogens. So if we had perfectly flat cyclobutane, we would really be in trouble because we have more hydrogens that are locked into a conformation, and in turn we would have more eclipsing interactions. So if we had planar cyclobutane, we would end up with a large amount of torsional strain. So to fix this, what cyclobutane does is it will adopt a puckered conformation. And that in turn, in this puckered conformation, it staggers our hydrogen substituents and minimizes torsional strain. This is a common phenomena for larger ring systems where the ring will pucker and adopt a 3-dimensional conformation to minimize these killer torsional interactions. So let's look at an example. So if we look at the puckered cyclobutane system and we look down one of our carbon-carbon bonds like so, as we can see, as a result of puckering and distorting from a planar system, our hydrogens are not quite eclipsed, and we in turn have weaker torsional strain. because we have a greater dihedral angle separating our substituents. Does that make sense? Does the reason behind why these ring systems adopt a 3D conformation make sense? It's to minimize torsional strain and minimize eclipsing interactions. Now, cyclobutane is slightly bent out of plane. One carbon atom is positioned about 25 degrees above the other. This bend increases the angle strain because in turn we have reduced our effective bond angles, but it decreases our torsional strain. And that payoff in terms of decreasing torsional strain is more than enough to compensate. Okay, so let's look at cyclopentane systems. Cyclopentane has less angle strain than cyclobutane. And interestingly enough, planar cyclopentane would have no angle strain. Now, that sounds good, but remember, when we have a planar system and we've locked in all of our hydrogens into this planar conformation, we end up with a huge amount of torsional strain. So then, the actual conformations of cyclopentane are non-planar. This minimizes our torsional strain. So again, we don't have planar cyclopentane. The torsional strain would be too much. So instead, we adopt a non-planar conformation that's called a quote-unquote envelope conformation to minimize our torsional strain. Again, as you can see, as a result of this puckering, if we look down one of our carbon-carbon bonds, as we can see, our hydrogens are not eclipsed anymore. So we have minimized torsional strain and torsional interactions between our substituents. Does this idea make sense? Does this idea make sense? So for cyclopentane, 4 carbon atoms are in the same plane, and the 5th carbon atom is above or below the plane. It almost looks like an envelope. So let me show you what this looks like. Give me one moment to put my model kit together. Here we go. So sorry, the camera's mirrored. Here we go. So as we can see, we have most of our carbons in the plane, and we have one of our carbons above the plane. Does everyone see how one of our carbons is pointing up above the plane? So let's showcase this as a side-on view. Let's remove this substituent to make it easier to see. Does everyone see how we have most of our carbons in the plane and we have this one carbon pointing out above the plane? Does everyone see that? Okay, now, if we look really carefully and if we look down one of our carbon-carbon bonds, let's arbitrarily look down one of our carbon-carbon bonds. So looking down this carbon-carbon bond right here, are 2 hydrogens, are they staggered or eclipsed as a result of this puckering? Are our 2 hydrogens staggered or eclipsed? Are they close together in dihedral angle or are they far apart? Looking at our 2 hydrogens. Looking down our carbon-carbon bond, Do we see a large or small dihedral angle? They're far apart, right? Does everyone see the separation in terms of dihedral angle? Does everyone see how these hydrogens are almost pseudo-staggered in a way? Does everyone see that? This separation between our hydrogens on our adjacent carbons? Does everyone see this separation in terms of dihedral angle? And that's a result of puckering. If I tried to make planar cyclopentane, here's planar cyclopentane, what do we notice about our dihedral angle? If we look down our carbon-carbon bond, what do we notice if we have a planar cyclopentane? Do we have a lot of torsional strain now? They're almost eclipsed, exactly right. So this puckering is really important. So you should make sure to draw your cyclic systems with this three-dimensional shape, with this puckering in mind. Really important. So cyclohexane. So cyclohexane is the most studied and the most prevalent cyclic structure in these sophomore organic courses. Substituted cyclohexanes occur widely in nature. The cyclohexane ring is free of angle strain and can adopt chair conformations with negligible torsional strain. So a chair conformation has alternating carbon atoms in a common plane and tetrahedral angles between all carbons. So allow me to show you a sample chair conformation. And you may want to try to put together a model of this chair conformation, as it's something that we are going to be studying in detail throughout this next chapter. This chapter can better be summarized as a detailed study of cyclohexanes and their conformations. Okay, so let me get the chair conformation set up. And I'd like you during this time to start putting together the chair conformation using your model kit. Okay, so here is an example of a chair conformation. So one thing that I'd like to draw your attention to, if we look at this from a side-on perspective, you'll notice first and foremost that one of our carbons is pointing up. So the model kit that we're looking at now, this is our carbon, one moment. This is our carbon that's pointing quote unquote up, while our fourth carbon, which is shown right here, is pointing down. Now, one thing that's really cool about this chair conformation is if we look down our carbon-carbon bonds, does everyone see how if we compare our substituents on our adjacent carbons, are these substituents staggered or eclipsed? Are these substituents staggered or eclipsed? They're staggered, exactly right. So the chair conformation, and the way to know that you've generated a reasonable chair conformation, is that as you look down each of your carbon-carbon bonds, all of your substituents on every carbon will be staggered. So if we keep working our way down the ring, we still see staggered. Keep working our way down the ring, again, still staggered. Continuing on, as you would expect, still staggered. Okay. So this is your typical chair conformation. Does everyone notice does everyone see that characteristic zigzag pattern where we have pairs of carbons pointing up and pairs of carbons pointing down? So we can often draw our chair conformations like so. The other chair conformation would look something like this. So we have pairs of parallel carbons pointing up and down. All of our substituents are staggered, and we've minimized our angular and torsional strain. The chair conformation is the lowest energy conformation for a cyclohexane because it's minimizing the torsional strain. All of our substituents are staggered, so we've minimized angular and torsional strain. And we can see that if we draw a Newman projection for our cyclohexane system, that all of our hydrogen substituents are staggered. Does that make sense? Okay, perfect. Now, cyclohexane can adopt a range of possible conformations, and it's important that we study these intermediate and other conformations in order to understand, in order to identify the lowest energy conformation and the energy barrier necessary to change conformations. Okay, so let's talk about how do we draw a cyclohexane chair conformation. So first things first, you draw two parallel lines slanted downward. So okay, once you've drawn your two parallel lines, you place the topmost carbon atom above and to the right of the plane of the other four, and you connect your bonds. Okay. Next, you place your bottommost carbon below and to the left of the plane of the middle four, and you connect your bonds. So your cyclohexane should look something like this. You have your two parallel lines and your topmost and bottommost carbon. You really want to practice drawing your cyclohexane chair conformations because you don't want to make an error in drawing your chair conformation and end up missing a key point from the drawing. So that's how you draw a cyclohexane chair conformation. And you may want to practice a few times drawing not only the first chair conformation, but also the second conformation, the second chair conformation, which is simply a mirror image of the first. So I'd encourage you to practice it just so that way when you're taking your notes, you're not spending as much time having to painstakingly focus on drawing your cyclohexane chair conformation. You can just draw it quickly and efficiently. Okay, so let's talk a little bit about substituents. Let's talk a little bit about substituents. So there are two types of substituents, axial and equatorial substituents. The chair conformation itself has two kinds of positions for substituents, axial positions and equatorial positions. Let me use some color coding. Let's use some color coding for that. So, as we can see, a typical chair cyclohexane has 6 axial hydrogens. Shown here, these are our axial hydrogens that are perpendicular to the ring, and 6 equatorial hydrogens that are parallel to the ring axis. So to show you a depiction of the axial and equatorial hydrogens. So here's our chair conformation. Does everyone notice, first and foremost, okay, here we go. Let me try to get the angle just right here. Okay, does everyone notice how for our axial substituents, which are the substituents in red, they're perpendicular to our plane. Does everyone see how our plane and our axial hydrogens are perpendicular to our plane? While our equatorial hydrogens are parallel to our plane. One of the hallmarks of the equatorial hydrogens is that they're parallel to your carbon-carbon bonds found in your ring system. So we have, for example, a carbon-carbon bond here, and the equatorial hydrogen is parallel to that bond. So as we can see throughout our ring, if we look at this from a top-down perspective, we have 3 axial hydrogens on one face of our cyclohexane ring, and then on the opposite face, we have another 3 axial hydrogens for a total of 6. If we look in the plane, we have, and we can clearly see our 6 equatorial hydrogens. 1, 2, 3, 4, 5, 6. So we have all 6 of our equatorial hydrogens in the plane. Does everyone see the axial and equatorial hydrogens from this perspective? Okay. So one thing I'd like to draw your attention to is that we have 3 axial hydrogens on the top face and 3 axial hydrogens on the bottom face. Likewise, for our equatorial hydrogens, we have 3 equatorial hydrogens that are pointing up and 3 equatorial hydrogens that are pointing down. And we'll elaborate on this idea more momentarily. So each carbon atom in a cyclohexane has 1 axial and 1 equatorial hydrogen or other substituent. Now each face of our ring has 3 axial and 3 equatorial hydrogens in an alternating arrangement. So let's talk about what we mean by that. So if we look at our structure from a top-down perspective, we see on the top face, we have 3 axial hydrogens pointing up. So I'll call these axial, quote unquote, up. Does everyone see how they're pointing towards you? Does everyone see how these 3 hydrogens are pointing towards you? You can also look at it from a side-on perspective. You can also look at it from a side-on perspective and see that in this structure, we clearly see that we have 1, 2, 3 hydrogens that are pointing up from the axial perspective. Likewise, if we look at the bottom of our ring, we see that we have 1, 2, 3 hydrogens on adjacent carbons that are axial pointing down. Does everyone see that from this model? Does everyone see the axial up and axial down hydrogens? So just as a refresher, the axial up hydrogens, 1, 2, 3. They're perpendicular to the plane, they're pointing up. We also have axial down hydrogens, 1, 2, 3. They're perpendicular to the plane and they're pointing down. Does that make sense? Okay, now for our equatorial hydrogens. So you may notice if we're looking at, for example, the following carbon, when our axial hydrogen is pointing up, what direction is our equatorial hydrogen pointing? Is this pointing up or down? How is this equatorial hydrogen pointing? It's pointing down, exactly right. And this occurs at alternating carbons. Alternatively, on the carbons, if we focus now on our adjacent carbon that is next door, as you can see, when we have an axial hydrogen pointing down, how is our equatorial hydrogen pointing? Is this equatorial hydrogen pointing up or down? So when our axial hydrogen is pointing down, how is our equatorial hydrogen pointing? Up, exactly. So we have a series of equatorial hydrogens that are equatorial up. Perfect. So we filled in all of our hydrogens in our cyclohexane ring. Let's talk about how you properly draw each of these axial and equatorial hydrogens to respect the fact that each of our hydrogens are either on the top or bottom face. They're either pointing up or down. So for our axial bonds, so we draw our cyclohexane ring. And then for our axial bonds, we draw a series of vertical lines. And we alternate with one set or three of our axial substituents pointing up, while 3 of our axial substituents are pointing down. To fill in our equatorial bonds, we draw a series of lines that are parallel to our carbon-carbon bonds. So we have one of our carbon-carbon bonds. So in turn, what we're going to do is we're going to draw our hydrogen that's equatorial parallel to that carbon-carbon bond. One shortcut, one method that I like to use is I like to remember that if I have a substituent pointing up the other substituent must be pointing down. So for example, if I have the following carbon-carbon bond, I draw my equatorial hydrogen pointing up. Likewise, if I have my carbon-carbon bond, I draw my substituent parallel to this carbon-carbon bond, and so forth. And with that, we've filled in each of our axial and equatorial substituents. Does that make sense to everyone? Does everyone see how our carbon-hydrogen bond, or our equatorial substituents, are parallel to the carbon-carbon bond that is adjacent? Does everyone see that? This process respects the relative stereochemistry of each of our substituents, and it ensures that we have the proper number of substituents or hydrogens on the top and bottom face of our cyclohexane. Any questions on this idea? Any questions on this idea? So again, this is another thing that you want to practice, as we'll be drawing a lot of cyclohexanes in this chapter. So let's keep going now, if we don't have any other questions. And one thing that I'd like us to do during this time, just to make sure that we understand how to fill in the substituents for a cyclohexane system, is I've given you the following blank templates, and I'd like us to use the annotate feature to fill in each of these templates with our axial and equatorial substituents. So I'd like us to take about 2 to 3 minutes, and I'd like a few students to break out the annotate tool, and then I'd like those students to fill in our axial and equatorial substituents, respecting the bond angles and respecting the relative position of our substituents. Perfect, perfect. And most importantly, the equatorial substituents were drawn with the correct stereochemistry. Good, very good. Practice really does make perfect. The more cyclohexanes that you draw throughout your problem-solving sessions, the more comfortable you'll be drawing out your substituents, and the less time you have to spend on the mechanics of drawing your cyclohexane, and the more time you can spend on analyzing your cyclohexane conformations. Does this make sense to everyone? Is everyone comfortable drawing cyclohexanes? They're going to be the centerpiece of our discussion, and these chair conformations are going to be the centerpiece of our discussion. So you should be able to draw them efficiently and accurately. Wonderful. So just to add in the instructor drawing, just so that way we have everything all in the same note set. So we have our 3 axial hydrogens pointing up, our 3 axial hydrogens pointing down, our 3 equatorial hydrogens pointing down, and our 3 equatorial hydrogens pointing up. Filling in our other chair conformation, we add in our axial hydrogens, and then we add in our equatorial hydrogens. Okay, perfect, perfect. So let's keep going now, and let's talk about the conformational mobility of cyclohexane. So the energetic barrier required for a change in cyclohexane conformation is low enough that cyclohexane can readily undergo changes in ring conformation at room temperature. The activation barrier is not extremely high, such that the kinetic energy associated at room temperature is enough to allow some of our molecules to interconvert and change conformations. Chair conformations will readily interconvert, resulting in the exchange of axial and equatorial positions via a ring flip. Okay. So let me put some labels. Let me put some labels on my So I'm putting together a model really quickly to show you this ring flip. And we'll talk a little bit about how this ring flip actually pans out in terms of your final chair conformation. Okay, so pretend now looking at the following ring system, we have our chair conformation all set up and ready to go. So the first thing that I want you to notice is that we have one of our carbons pointing up and the other carbon pointing down. Does everyone see that from this side-on perspective? That one of our carbons is pointing up and the other one of our carbons is pointing down. Does everyone see that from that side-on perspective? Okay, so in a ring flip, in essence, we're going to take the carbon that is pointing up and we're going to move it down, and the carbon that is pointing down, we're going to move it up. So we'll talk about the exact steps, but I'm just going to show you what happens as a final process. So after the ring flip that I've just executed, first, does everyone notice how our cyclohexane zigzag is now pointing in the opposite direction? Does everyone notice how our cyclohexane zigzag is now pointing in the opposite direction? Our substituent that was down is now up. What else do we notice? I have my axial and equatorial substituents color-coded. Notice, where is this red axial substituent now? Where is this red axial substituent now? Is it up or down? Or let me rephrase. Where is this axial substituent still axial? Is this axial substituent still axial? Looking at this substituent right now. Is it axial or equatorial? It's equatorial. So let me just show this to you one more time. So here's our starting ring. Here's our starting cyclohexane. As we can see, one of our carbons is up, the other carbon is down, right? Now, as we see, we have our axial hydrogen. It's pointing up, right? It's axial pointing up, right? So if we circle this, so I'm going to star these two carbons. So we see we have axial up and equatorial down, right? Okay, so now what we're going to do is we're going to bring our carbon that's pointing up and we're going to shift it to pointing down, and we're going to move the carbon that was pointing down and we'll shift it to moving up. We'll talk about the intermediate steps momentarily, but what I want you to appreciate is after the ring flip, after this ring flip, first, as we notice, the orientation of our cyclohexane ring has changed, right? It's now pointing in the opposite direction. And most importantly, what happened to our axial substituent? Is our axial substituent still axial? What do we see? Where's our axial substituent now? It's equatorial, exactly right. Now, what's really important to keep in mind, here as well is that it's now equatorial. Yep. So it's equatorial pointing down. Oh, sorry, it's equatorial. And now my question to you is this hydrogen, when it's equatorial, is it still pointing up? Is this hydrogen still pointing up when it's equatorial? Is this hydrogen still pointing up when it's equatorial? Yes. So it's equatorial, but it's still pointing up. And this is really important because even though the relative position in the ring has changed, it went from axial to equatorial, the stereochemistry, whether it's on the top or bottom face, has not changed. It's equatorial pointing up. Likewise, our equatorial substituent after the ring flip is now axial, but it's still pointing down. So stereochemistry, the relative position of our substituents in 3D space, is preserved during a ring flip. Does that make sense to everyone? Does the model kit help you see what's going on in the ring flip? So we're bringing our carbon that's pointing up down, and our carbon that's pointing down, we're bringing it up. As a result, all of our axial substituents become equatorial. All of our equatorial substituents become axial. Now, it's really important that you keep track of your carbons, because if you change the position of your substituents, you could actually end up drawing constitutional isomers, or even worse, drawing stereoisomers or enantiomers. So I like to label my carbons 1 through 4. I move carbon 1 down and carbon 4 up. As a result, all of my equatorial substituents become now axial, and all of my axial substituents now become equatorial. Notice, and this is really important, that the stereochemistry, whether your substituent is pointing up or down, does not change during a ring flip. So make sure to number your carbons. So I have it 1, 2, 3, 4, 1, 2, 3, 4. And note that when you're drawing your ring flipped cyclohexane ring, that carbon 1 is now pointing down and carbon 4 is now pointing up. Now, because the two chair conformations have different axial and equatorial substituents, one chair conformation may be energetically favored. And that is going to be what we're going to focus on in this chapter. Now that we can see that there are multiple different conformations and we can draw those chair conformations, we can then assess which chair conformation is lower in energy and favored at equilibrium. Does this idea of ring flips, does the basic mechanics of a ring flip make sense? Any questions that I can address? Okay, let's keep going now. So what we're going to practice next is drawing chair conformations of cyclohexane using dash wedge notation. Now, Students often get intimidated by this concept, even though it is very straightforward if you have your model kit set up. So this is partially why I like using a model kit, because it makes dash wedge notation very easy to see. So how does dash wedge notation work? Okay, so here is a chair conformation of a cyclohexane ring. When we have a wedge bond, such as shown here, that's telling us the bond is pointing up out of the plane of the page, okay? So looking at our bromine in this chair conformation, is this bromine pointing up or down? Is this bromine pointing up or down? It's pointing up, exactly right. So to showcase this and to match this with the model that we have, we currently have, let me set my cyclohexane in the right arrangement. So then I'm going to label this carbon as carbon number 1. And at this carbon number 1, the substituent that is pointing up is going to be axial. So that would look something like this. Does everyone notice how the substituent at carbon 1 that is pointing up is axial? Does everyone see that? Okay, now I'm going to do a ring flip. So I have carbon 1 right here, and I'm going to bring my carbon 1 down, and I'm going to bring carbon number 4 up, okay? So I'm going to execute my ring flip. I'm going to bring carbon number 1 down and carbon number 4 up. So that gives us the following structure. So we have carbon number 1 pointing up and carbon number 4 pointing down. So now when we redraw our chair conformation, we have carbon number 1, 2, 3, 4. Okay. And as we notice, this bromine, is this bromine still pointing up? Yes, except this time in our other chair conformation, it is now equatorial. So in our two chair conformations, we'll either have the axial up bromine or the equatorial up bromine. It's really important that you respect the stereochemistry, the relative position of the bromine, whether it's above or below the plane of the page, and that you respect the connectivity of atoms. So even during a ring flip, the stereochemistry is still the same. Wedge pointing up. Does that make sense? Can everyone see that with the model kit? Perfect. So a dashed bond indicates that the bond is pointing down below the plane of the page. Okay, so let's showcase that. If possible, I like to start counting at carbon 1. So I'm going to arbitrarily label this carbon as carbon 1. Okay, so a wedge bond means that the bond is pointing down below the plane of the page. So here's a model of one of our chair conformations. And my question to you is, looking at, so here's carbon 1 and here's carbon 4. My question for all of you is, looking at our substituent, looking at our alcohol, is that alcohol pointing up or down? Is this alcohol pointing up or down? It's pointing down, exactly. So this is an equatorial and down substituent. In this current conformation, if we have our carbons labeled as such, is there any way for, in this current conformation, for this alcohol that's pointing down to be axial? In this current conformation, just as we have this model here, is there any way for us to get this substituent axial? Clearly not, right? We would have to look at it from either a different perspective, or we have to undergo a ring flip. So to get this alcohol in an axial position, that occurs after a ring flip, where again, we bring carbon number 1 down and carbon number 4 up. Does everyone see how the arrangement of our carbon atoms matches this chair conformation drawn? Sometimes you may have to like squint your eyes a little bit to start to see the parallels, but does everyone see how the arrangement of the carbon atoms matches this chair conformation shown here? Okay, so we're going to undergo a ring flip now. We're going to bring carbon number 1 down and carbon number 4 up. Okay, so we've completed our ring flip. Carbon number 1 is now pointing up. Carbon number 4 is pointing down. And my question to all of you is, where is our alcohol now? It's still pointing down, that we can see for sure. It's pointing down. Everyone can see that. Is this alcohol now axial or equatorial? It's axial. This alcohol is axial, pointing down. So this is how you draw the chair conformation for a cyclohexane ring system containing both a dashed and wedge substituent. So we went from dash wedge notation into a chair structure that respects the stereochemistry of our substituents. Does that make sense? Does that make sense to everyone? Perfect. Do not mess this part up. There are problems that you'll see throughout this chapter where if you draw the wrong chair conformation, your answer will be completely off. And as well, one thing I really want you to respect is that if it's a wedge, it's pointing up. So you need to make sure to respect that stereochemistry, even after a ring flip. And make sure to always respect the carbon numbering. Carbon 1 goes down, carbon 4 goes up. If you move your substituents around, you'll end up drawing mirror images, which are known as enantiomers, and you don't want to do that. Okay, so what I'd like you to do is I'd like you to draw the chair conformations of the following molecule. So don't be shy to break out the annotate tool, and we can split the work among 2 students. So let's have 2 students chime in and draw the chair conformations of the following molecule. And this will be the last example for today. So let's break out the annotate tool and let's try to get 2 chair conformations for the following molecule. And it doesn't matter where you put that thiol group, as long as you're respecting its stereochemistry. I find it's easiest to put it on carbon 1, yep. And so it's a wedge, so where's that thiol gonna be? So what does the wedge tell us? Yep, the wedge tells us that our substituent is pointing up, and at carbon 1 it would be axial. Exactly right, very good. Would someone like to propose the other chair conformation? So after a ring flip, what would the other chair conformation look like? Let's try to get another student providing the alternative chair conformation after a ring flip. What would it look like after a ring flip, where we bring carbon number 1 down and carbon number 4 up? What would the ring flipped form of this structure look like? Okay, so we've drawn our ring flipped cyclohexane skeleton, and we've drawn our ring flipped chair conformation. Now, where does that thiol end up? Where does that thiol end up? So if this is carbon 1, yep, carbon 1 ends up right here, pointing down, and the thiol is still pointing up. This is really important. When you draw ring flips, it's really important that you respect the stereochemistry. Wedge, the group is pointing up. Does this make sense to everyone? Is everyone comfortable with these examples so far? So, as it's the end of our scheduled lecture period, we'll stop the recording for